The answer is really simple, so please don't lose sight of that. The answer is that the current contributions to PM downwind of Oceano Dunes has a very small fraction of dust. So the answer in the end is 14%, and I'll tell you how I got there. So just to introduce myself, I'm a distinguished professor of atmospheric chemistry at the Scripps Institution of Oceanography at University of California, San Diego. And that means that I have spent about 30 years measuring, modeling, and analyzing aerosol particles in our atmosphere. And my training for this was I have degrees in chemical engineering, a bachelor's from Stanford, and a PhD from Caltech. And I've been named a fellow of the American Association of Aerosol Research and the American Geophysical Union for my work on aerosol research. In order to figure out the part that could be dust, we set out to measure the chemical composition to know how much is actually dust. The BAM, or Beta Attenuation Monitor, run by SLOAPCD at CDF, measures mass by absorption of beta radiation, and that's a fancy way of saying it measures the total amount of suspended stuff from all types of all sources and all chemical components. And it sometimes includes water that remains even though in the instrument you heat up the particles a bit. And PM10 and PM2.5 are the federally regulated metrics that include both natural and man-made sources. And I'll be also talking about the federal reference method is what is known as gravimetric weighing, which is what we had before BAM. And so before BAM, you had to collect a filter and you had to weigh it after leaving it for 24 hours at a controlled low humidity of 35%. And that took forever and you couldn't get hourly information. And so BAM has a lot of advantages and it's a federal equivalent method. So why do we need to measure the mineral dust? PM has many sources. We've heard about a number of them today. NOx is a source of nitrates in particles. VOCs, or reactive organic gases that we're working hard to control, those contribute organics. Sulfates also contribute. And there are many different kinds of dust. There's road dust and there's agricultural dust, and then there is dune dust. So we would like to be able to separate those. It's harder to separate the types of dust from each other. So here we're going to give a very conservative estimate. We're going to measure the total amount of dust as being the maximum that could be from the dunes. We picked to sample at the maximum time of emission during the day, which is in the afternoon, because that's when the wind is high. And we didn't try and distinguish between other dune areas. So this has potentially got contributions from other nearby beaches or dunes. And we picked the windiest months of May and October. And so we're really looking to capture that worst possible scenario. This is a NASA simulation of worldwide emissions of everything. In orange and red is the dust. And you can see there's this huge source from northern Africa, and that dust is blown all the way over the Caribbean, where I've also measured dust over the Caribbean. I'll point out that the green are the carbonaceous contributions from organic and black carbon. The blue is sea salt, and the white is sulfate. And so what the point here is that you will see in this simulation and the days running at the top, day-to-day differences at any one location in what's contributing to the PM. Is it dust? Is it sulfate? Is it sea salt? Is it something else? And so there's going to be variability. So even though I'm giving you that one answer of 14%, there's, Monday is different from Tuesday, and that's going to differ from Wednesday. So I mentioned that the BAM sometimes gets water stuck on it. And that's because in CDF, at the CDF site, the relative humidity varies from about 60% to 90%, and there's a daily cycle that kind of mirrors the wind speed, but it also mirrors the temperature. So in the afternoon, during the hotter times, humidity is a little lower, but the entire time it's much wetter than 35%, which is the regulated humidity you're supposed to measure at. And so the BAM humidity equilibrated, but only for 1 hour, not 24 hours. And the manual for the BAM instrument tells you that the sample relative humidity, if the sample relative humidity is excessive, which they define to be 50%, then the particulate on the filter can adsorb moisture, and the measured mass will increase due to water. If you go to 2021 in spring, you can see our dust fraction. This is the 14% where we can see. So there is year-to-year variability because the wind varies year-to-year. But on average, what we see for the dust fraction is here. And PM10 is 11 plus or minus 8 and 14 plus or minus 10%. So again, this is the 14 plus or minus 10% on high PM days of what dust is contributing. And this is what was peer-reviewed and published by my graduate student, Savannah Lewis, with myself and others as co-authors. The highlights at the bottom here are that the mineral dust contributes an average of at most 14% of BAM PM10 measured downwind during windy afternoons. The average afternoon PM 2.5, which I'll remind you is the one we think actually is more important for health effects, also included about 14% dust, 9% sea salt, as well as non-sea salt sulfate and organics. The unidentified fraction that's associated with those change in humidities is a big open question, but it doesn't change how much dust there is. Dust is super standard and easy to measure. Its chemical composition is not in doubt. It's really pretty simple and has been known for quite some time. So the unidentified fraction doesn't change how much dust there is. The BAM to gravimetric differences are fascinating, and that's actually, we're not the only ones to report those humidity and temperature dependencies. They're all over the literature. Back to what I think is most of interest, it's 14% dust. And thank you for your attention, and I'm happy to answer any questions.